Some people are still working in. I think we just did a 1 minute.
Okay. Do you have any announcements before, or you just want me to start?
No, I think it is.
Hello, everyone. Thanks for coming to the seminar today. It's my pleasure to introduce our speaker, Dr. Kelly Sanks. She is a postdoctoral scholar at Tulane, working in earth and environmental sciences. Her background is in geology. She got her bachelor's degree at Illinois State, and then went on to get her master's and PhD at University of Arkansas. And so she focuses on coastal deltaic systems, and I think that'll be of interest to all of us. And she does it from the geology perspective. So that's going to be quite an interesting talk. So let's welcome Kelly.
Okay, thank you for the introduction, and thanks everyone for coming. I'm excited to talk to you guys today about some of my work for my PhD, as well as some work that's related that I'm doing at my postdoc, and it's all sort of focused on organic carbon in deltaic and wetland systems, specifically in coastal Louisiana. So, oh no, does this not work? Okay, thank you. So my kind of broad research interest is the interaction of river deltas and the vast wetland platforms that make up a lot of the large global river deltas we see. So I'm going to show you some images of some modern delta wetland interactions. Here we have the Ganges Brahmaputra Meghna River Delta, which is in Bangladesh. And we can see that we have a large river that is flowing and transporting sediment to the coast. Some of that might get deposited in the channel itself. Some of it might get transported offshore, and some of it gets transported alongshore. And then in this case, back up these tidal channels. And we can see that these tidal channels, as well as the large main channel, is encompassed around these very large. Doesn't work anymore. Okay, these very large wetland platforms. So we have that in this river delta. Here's another aerial image. This is of the Amazon River Delta, and we see a similar thing. We have these large distributary channel networks, and in between the channels, we have interdistributary bays that are encompassed by wetland platforms. Although it might be a different type of vegetation, we have similar interaction between these two processes. And then here's the Mississippi River Delta, which I'm sure we're all familiar with. We have two main rivers, the Mississippi River and the Atchafalaya River. Both rivers transport a lot of sediment to the coast, as you can see with the large sediment plumes in the Birdsfoot and the Atchafalaya and Wax Lake River Deltas. And then we have a large expanse of wetland platforms, which either receive sediment somehow from these river sources, or they can accumulate their own sediment in situ from the primary production of the vegetation that encompasses those platforms. And that makes up organic soil. we see this in modern settings, but we also see this in ancient settings as well. So here we have a outcrop from the Fort Granger Delta Complex. This is in eastern Kentucky, and we can see this very large coal seam here, which would have been a wetland platform when it was formed, and that is interbedded with these lenticular channel sands. And so this interaction of river deltas, physical processes in river deltas that transport plastic sediment with these wetland platforms that produce organic sediment has happened throughout Earth's history. But often when we study river deltas or when we study wetlands, we don't often couple these processes together. So that's what I'm really interested in understanding, is how the interaction of these two processes form river deltas and how they contribute to their evolution on both short time scales as well as long time scales, which can tell us a lot about management and restoration, which is really important now as we're facing sea level rise, and a lot of our wetland platforms and our river deltas are shrinking due to a combination of anthropogenic impacts that they face. So I'm going to look at some different questions. The first one we're going to look at is, how does organic sediment influence the long-term evolution of dynamics of river deltas? And I study this with experimental river deltas, with the hypothesis being that deltas evolving with in situ deposition of organic sediment will be larger compared to those evolving with just fluvially delivered sediment, and that will translate to different surface processes happening between two experiments, one that has this organic deposition and one that doesn't. So if you're unfamiliar with experimental river deltas, they're commonly used in the stratigraphic and sedimentology community within geosciences to study river deltas. And so here I have two aerial images of two different experiments. The one on the left is labeled control. That's a classic physical delta experiment that just evolves with fluvially delivered sediment. And so there's no interaction with like waves and tides, and there's no kind of wetland dynamics in that experiment. And it's run under a certain set of conditions. And so we compare that experiment to another experiment, which is shown on the right, which is the treatment experiment. And that experiment evolves under all of the exact same conditions, except we add a proxy for organic sediment accumulation. And that proxy is just an elevation rule-based model where we relate primary production of wetlands to their elevation relative to sea level. So here's two images of the experiments, and we can see just visually that they look quite different. I've plotted three contour lines on here, 5 millimeters, 0, which is sea level, and then -9 millimeters relative to sea level. And we can see that the shape of these contours, how they go up the river channels, is very different. So the benefit of using physical experiments to study this question is that we can run them for really long periods of time. So we run them for over 500 hours. And if you scale that time up to a field setting, that would produce about 1 million years of stratigraphy. So running these experiments is much faster, obviously, and you can control the variables that you want to understand. And because we can run them for a long period of time, we can capture autogenics of the system and any kind of stochastic variability. So any mean parameters we're estimating from these experiments can be considered representative of the two systems. And so we can also collect a lot of very high precision data using this setup. And mostly the data I use is LiDAR scans, which gives you elevation, millimeter precision elevation, and channel maps, which just map out where the channels are. But we also can use a lot of other data. We section these experiments and we get stratigraphic cross sections. And so we can use that to understand the subsurface as well, which is not something that I am specifically working on. But so this is part of my dissertation, which was done with all of these collaborators here. Sam Zapp, who's in the audience, also worked on this. He's a PhD student here now. So let's look at some of the data from these experiments. This graph is showing the area in meters squared on the y-axis versus the time in hours on the x-axis. And the next few slides, the blue lines are going to correspond to the control experiment. So again, that experiment just has fluvially delivered sediment, and then the green is going to correspond to the treatment experiment, which that has both fluvially delivered sediment as well as the organic sediment. And we can see if we look at the dark lines on the top, that is the delta top, the dark green and the dark blue. We can see that the treatment experiment is larger than the control experiment. And then the two lighter lines on the bottom, that corresponds to the marsh window. So that's just the window, the elevation band where we added this organic sediment in the treatment experiment. And we can see that that's even more drastically different between the two experiments, where the treatment experiment has about twice the amount of elevations in that band as compared to the control experiment. So this suggests we have sort of changed the elevation distribution of the two deltas. And so we see here both the total delta area and the area that's near sea level are larger in the experiment that has organic sediment deposition. And that also relates to these elevation profiles, which I just mentioned. So this graph here is showing the mean elevation relative to sea level on the y-axis versus the radial distance from the entrance channel on the x-axis. So if you look at the right here, this is where the apex of the delta is. And then as you move this way, you're moving distally into the basin. And we can see that the two profiles look pretty different. And most notably, in the treatment experiment, we have this steeper slope above the marsh window, which is that area where we added this proxy. And once the experiment enters that elevation band where we deposit that sediment, the slope decreases and you get a very pronounced slope break right near the marsh, where the treatment experiment enters the marsh window. And this is seen in a lot of global systems as well, notably the Mississippi and the Ganges. And so this profile seems a bit more representative of global settings. And we see this slope decrease near sea level in the treatment experiment. And we actually get the opposite. If you look at the blue line, which is the control experiment, the slope actually increases in that window. So it looks like this might be more representative of field systems, and we can actually scale the elevation distribution to kind of test that. So here I have a probability distribution function of normalized elevation. The normalized elevation is just the elevation divided by channel depth. That allows us to compare across scales. This is a common process that's done when you're using experimental settings and you want to scale up to field settings. You have to normalize the variables. So I've plotted 4 global deltas: the Mississippi River Delta, the Ganges, Brahmaputra Meghna River Delta, the Mekong River Delta, and the Rio Grande. And we can see that there's this peak in elevation in all of those settings near sea level. And we also get that signature in the treatment experiment, but we don't see that in the control experiment. So the elevation distribution of a delta with organic deposition is more analogous to field scale deltas. And so it's really important that when we're looking at restoration strategies and building things like sediment diversions, that we really include the dynamics that will come from this organic sediment deposition that's not often included in specifically in experimental studies. So now we're going to look at modern rates of organic carbon sequestration in coastal Louisiana. And before I kind of tackle this question, I just want to go over some terminology that's commonly used in coastal environments. The first is, what is blue carbon? So this is kind of like a hot topic word that is used recently, and it's simply just organic carbon that's stored in coastal environments. But I just want to note here that mostly when you see blue carbon and refer to blue carbon in the literature, it's specifically relating to these 3 systems, which are vegetated coastal ecosystems, tidal marshes, mangroves, and seagrasses. And sometimes as well, like deep ocean environments, but often settings like river deltas or channels or mouth bar deposits, crevasse plays, things like that that are formed by river deltas are not included in this categorization. And the reason blue carbon came about, this term originated, was because it was to sort of highlight the importance of these 3 vegetated ecosystems in global carbon sequestration in the global carbon budget. Because they've often in the past been overshadowed by their terrestrial counterparts, which are terrestrial tropical forests that are termed green carbon. And that's simply because terrestrial forests make up a lot more area than these coastal ecosystems. However, it's recently sort of been shown and known that these three types of coastal ecosystems store organic carbon in their soils at much higher rates per area than do terrestrial forests. And so that's where this kind of blue carbon sequestration terminology came from. However, there's also some work that suggests that river deltas are also better at storing carbon in their soils than terrestrial forests, but they're not often thought about in terms of blue carbon sequestration or any kind of carbon offset projects where you try to use a coastal restoration strategy for storing blue carbon, for example. And so my goal sort of is to quantify how well river deltas can store carbon in their deposits. Here's another table here, just sort of illustrating the same thing. These are the three kind of blue carbon systems, and we see that they store around 200 tons of carbon per kilometer squared per year. Those rates vary depending on where you are, like location-wise, as well as studies that are global versus site-specific, but they roughly store around 200 tons of carbon per kilometer squared per year. A more recent study has shown that the modern Louisiana wetlands might store significantly more carbon than that per area. And then there's sort of varying rates of carbon sequestration for what would be river delta deposits. So for the Wax Lake Delta subaqueous deposit, we've seen that that stores about 250 tons of carbon per kilometer squared per year, which is sort of in the same realm as the blue carbon systems. And there's other studies that suggest maybe in the Amazon River Delta clinothem or a clinothem preserved in the rock record that it might be significantly lower than that. So we want to constrain this specifically for the Louisiana settings and to look at how well the mid-baritaria sediment diversion might be able to act as a carbon sink. So first we're going to look at, and it's pretty easy to calculate a carbon accumulation rate. So you just need three variables if you want to calculate this. The first is vertical accretion rate, the second is the sediment density, and the third is the total organic carbon. And it's pretty easy calculation. The organic carbon accretion rate, accumulation rate is just equal to the vertical accretion rate times the bulk density times the organic carbon content. And so this makes this pretty easy to calculate. You just need some sediment samples and a little bit of analysis, and you can get this pretty easily. So we're going to come back to now look at the modern rates of organic carbon sequestration. And the hypothesis here is that carbon accumulation rates will be largest in directly nourished or active delta lobe environments as compared to their wetland counterparts, which don't have a direct source of river sediment input. So we use the CRIMS, the Coastwide Reference Monitoring System, to look at this question, which if you're not familiar, is just a network of monitoring sites in coastal Louisiana that was set up by the USGS and the Coastal Protection and Restoration Authority. And this is some work I did as part of my dissertation with Dr. Nathani and Dr. Shaw. So here I'm showing a map of coastal Louisiana, and all of these black dots are CRIMS sites, and they have information already freely available. That is the vertical accretion rate, the sediment density, and the organic material component. And so those are all the variables we need to calculate organic accumulation. So that's really cool. And so we use what's called Bayesian kriging, which is a type of spatial interpolation to calculate those sediment properties throughout the entire coast. So I have three maps here. The top map A is showing the accretion rate. The middle map here is showing the bulk density. And then the bottom map here is showing the organic fraction interpolated across the coast using a 1 kilometer grid. And we see that the bird's foot area, so this directly nourished area, has really high accretion rates, really high sediment bulk density, and really low organic fraction comparatively to the rest of the coast. And that kind of holds true as well for the other directly nourished area, which is the Chapel and Wax Lake deltas. And then we see, these large wetland platforms in the Cheniere Plain have the opposite signal. So they have a lot of organic sediment or a lot of organic fraction, but they have really low accretion rates and low bulk densities. So if we want to calculate carbon accumulation rates, we essentially, or there's sediment accumulation rates, we just need to multiply these variables. So we can get total sediment accumulation rate by multiplying vertical accretion times bulk density. And we can get organic sediment accumulation rate by just multiplying all three. And then you can tease out the mineral sediment accumulation rate by subtracting the two. So those are these maps here. The top map shows total sediment accumulation. The middle shows mineral sediment accumulation, and the bottom shows organic sediment accumulation. And really notably, we see that in the bird's foot, which is the main directly nourished lobe, that all three of those accumulation rates are high compared to the rest of the coast. So despite the bird's foot having really low organic fractions, it still has higher organic sediment accumulation rates because it has just much higher vertical accretion rates than these wetlands here, which are primarily accumulating with just organic sediment accumulation. So this is organic sediment accumulation. The CRIMS data has organic material, and that's what this is made from, but there's other things besides organic carbon contained within organic material. And so if you want to calculate organic carbon accumulation rate, there's sort of different methods for that. Main one that's used pretty commonly is just using a conversion factor. And there's lots of different conversion factors. A common one is 0.58. So 58% of the organic material is organic carbon, and another one is 0.45. So 45% of the organic material is organic carbon. And that's how, if we remember back to that first table I showed, that's sort of where that 372 tons of carbon per kilometer squared per year for the modern wetlands, it comes from using one of those conversion factors. So one of the PhD students at Tulane, Jose Silvestre, is working on a different method to not rely heavily on those conversion factors, which I'll kind of show later, we don't think work very well across sediment types. And so he's produced this preliminary map here, also using Bayesian kriging, which shows that the bird's foot has about 600, or accumulates about 600 grams of carbon per meter squared per year, as compared to the Chenier Plain, that is maybe about 6 times faster. So this higher organic accumulation rate holds true when you look at total organic carbon. And so these active deltaic environments are actually really good at sequestering carbon compared to their just tidal wetland sites. And the average rate here is about 300 grams of carbon per meter squared per year, which we see is lower than that variable I showed initially. And that's because that other number kind of relied heavily on these conversion factors. And then lastly, we see this graph here showing organic material on the y-axis versus mass deficit on the x-axis. And we see that the directly nourished areas are closer or in a sediment surplus. So these areas are less susceptible to losing land due to rising sea levels, at least in coastal Louisiana. So not only do the directly nourished areas sequester carbon faster, but they're also less likely to lose land as sea level rises compared to their indirectly nourished wetland platforms. And so if we really want to preserve or have environments that are storing carbon on long time scales and taking it from the atmosphere, using them sort of as carbon credits for restoration systems, it appears like a restoration strategy that is kind of mimicking these deltaic deposits would be the best at storing carbon and keeping land. So lastly, I'm going to talk about some of my postdoc work, which is sort of doing a similar study where we're looking at organic carbon, but we're looking at it over the Holocene, and we're looking at different deposits preserved in the stratigraphic record in coastal Louisiana. And our hypothesis here is similar to the last study, that deltaic deposits preserved in the stratigraphic record will store more carbon will have higher carbon accumulation rates than bays and wetlands. So we have 2 field sites here. The first is Barataria Bay, which we did some field work last spring, where we collected fiber cores and hand cores from both wetland sites as well as open water bay environments. And Kevin Shu is also working on this project as well, but I'm not really going to talk about that data here. If you're unfamiliar with where Barataria Bay is, it is the site of the proposed Mid-Barataria sediment diversion. So it's just about 40 miles south of New Orleans. And the goal is to engineer what would be sort of similar to a natural crevasse splay to build land in Barataria Bay. And the projected land area is shown right here. So I'm going to zoom into that. Here in our study had 5 different transects that are going radially outward from that entrance, where we collected 10 cores from different environments. On the next slide, I'm going to show some of our stratigraphy from the Vibra cores. Right now, we are only able to use our water and bay cores due to like really high compaction in the wetland site. So we're going to do some more field work this spring to try to not have that happen. So here are 4 of the cores. These aren't in the same transect, so you can't use this to make like a cross section. And oh, sorry, these numbers don't really matter at the top, but we have 4 different cores here that we're working with, and I'm showing the stratigraphy. The white and the brown, that is going to be mucky or peat material, so high in organic content. The orange, the yellow, and the red is really coarse-grained sandy material, so that's going to be either a channel, a mouth bar, or crevasse clay. And then the green material, that's clays, which is often like a bay environment and typically has some like Rangia shells. And the goal of our study is to determine carbon accumulation rates throughout these cores. So we need to calculate bulk density, total organic carbon, and then we also need to know the sedimentation rate, which we are getting from both optically stimulated luminescence dating and carbon-14 dating. The black dots here are showing the carbon-14 ages that we already have, and the black dots are showing ones that we've sent to the lab. I was hoping to have those ages back, have a really good sedimentation model, but I haven't got that data back yet. So fortunately, I'm working with limited data here. And then our collaborator, Liz Chamberlain, is doing OSL dating on the bottoms of these cores where we have sand deposits. So we'll be able to have a sedimentation rate throughout the core that changes as you shift environments. And so what I've done so far is I've opened these cores and I've taken measurements of sediment bulk density and total organic carbon, as well as organic material every 5 centimeters throughout all the cores. So here's just one of the cores. It actually corresponds to this one right here. And we can see from this, you can see from this image here, we've got lots of peat and muck, and then it's underlain by some finer grain material that's clay, likely from a bay deposit, and then that's underlain by really sandy, coarser grain material that's from either crevasse layer or mouth bar. And we're going to look at this graph here, which is depth on the y-axis versus organic material, which is the gray line, or total organic carbon, which is the black line. And we see that the really nice, pristine peats have the highest carbon rates, and then some of the muckier environments have less carbon. But then when you get into this caustic material down here, we have even less carbon. So that's sort of similar to what we're seeing in the modern wetlands and deltaic environments right now in coastal Louisiana. And I've calculated organic material and organic carbon because I want to calculate these conversion rates from organic material to organic carbon to see if they can be used as a good predictor of how much organic carbon is in the soils. And then our second site for this project is the Lafourche Delta Lobe. Liz Chamberlain has worked extensively at this study site, and she has really good chronology. She knows the environments really well. And the Lafourche Lobe contains a crevasse clay as well as a mouth bar. So we have lots of different environments here that we can work with. So we don't need to do any ages for this, but we did need the sediment properties. So we went to the Lafourche Lobe and we collected sediment samples every 10 centimeters to get total organic carbon and bulk density. If you're unfamiliar with the Lafourche lobe, it was the active Mississippi Delta lobe about 600 to 1600 years ago. It's located just west of the modern subdelta. And our site specifically is located right here along one of the crevasse splays of the Lafourche, and it's called Dulac. And here is a cross section of the stratigraphy in that area. We can see we have a crevasse split at the top, followed by a flood basin or a floodplain, and then followed by a mouth bar, and then some other deposits below. And we've got some good constraints on the ages there. And there's a couple more in the middle here from a later study. So I want to address first if carbon, these commonly used conversion ratios work well across environments and sediment types. So these two box plots are from Barataria Bay on the left here in Lafourche lobe, and the y-axis is the LOI to TOC relationship. So essentially the organic material to organic carbon. And so if the value here is 0.4, that means 40% of the organic material is organic carbon. And I've separated this by sediment type, and we can see that for really pristine peats to sort of more mucky environments, that relationship decreases, and that continues to decrease as you move from clays to sands over here. And it's there's a very drastic difference between peats and kind of deltaic sediments. And that holds true for the Lafourche lobe as well. We get a decreasing relationship for this conversion rate. And so I'm going to plot some of the commonly used conversions on this graph here. The first, Sire et al., which showed that modern wetlands in coastal Louisiana, you can use about 0.45 as the relationship. And that sort of works, but not for all the types of wetland material. And it definitely doesn't work in the Lafourche lobe. And then there's another commonly used one, which is actually the one that was used in the previous modern Louisiana wetland carbon accumulation study. And that's 0.58, that's used for terrestrial and coastal ecosystems kind of interchangeably. And that doesn't really fit for any of our data. So it's best if you want to calculate carbon accumulation rates to actually directly measure the total organic carbon, which is pretty easily done just using elemental analysis in the lab. It does take a little bit longer than measuring organic material with loss on ignition, but it's a lot more accurate, especially if you're working with lots of different sediment types and across different systems. So the next box plots are just showing the total organic carbon. And again, we get sort of the same signature we saw in the modern systems, where you have more peaty environments, you get a lot more organic carbon. And when you get into plastic environments, you have less carbon. And that's the same in Barataria and Lafourche lobe. Interestingly, the Lafourche lobe has a lot less carbon in its peat sediments than the modern, the Barataria Bay sediment, despite them being similar ages. So we're going to use the Lafourche lobe as an analog for carbon burial rates via sedimentation from the mid-Barataria sediment diversion. So I'm just reorienting you again. We have this nice preserved crevasse splay deposit in Lafourche, and that's sort of what this mid-Barataria sediment diversion is aiming to mimic. So we can use what we know about the sedimentation rates and the carbon accumulation in Lafourche lobe, sort of predict how much sediment, how much carbon the mid-Barataria diversion might sequester. And so here, going back to this cross-section of our area in Lafourche, we have carbon accumulation rate on the x-axis, and then the y-axis is depth, and I've drawn these lines to sort of correspond to the section. So we see in this borehole here, our crevasse splay and our flood basin accumulate similar rates of carbon, and the mouth bar has really, really high rates of carbon accumulation, although there's lots of uncertainty on that because the sedimentation rate in mouth bars is just very rapid. And then we move a little bit further east, and we actually see the crevasse splay here accumulates a little bit less sediment than the flood basin. And then again, the mouth bar has really high carbon accumulation rates. And so here's probably a little easier graph to digest. We have two models, a low sedimentation model and a high sedimentation model. And we see that carbon accumulation rates decrease in the peats through the classics, but then once you get into the sandy material, which is characteristic of the mouth bar, some of the crevasse clay, you actually increase your carbon accumulation rate, and it's quite a bit higher than the peat material. And so that sort of makes sense with what we're seeing in the modern systems as well. So deltaic deposits can be very good at storing carbon. We still need to fine tune this sedimentation model to get a little bit less or a little bit higher precision. But to go back to this first table, the modern study that we have shows carbon accumulation rates around 300 tons of carbon per kilometer squared per year, which is work that Jose is working on. And that's, again, lower than this previous study, which also used the CRIMS data, but relied on a conversion factor of 0.58, which I showed doesn't work very well, at least in Barataria and Lafourche lobe. And then our Lafourche lobe crevasse clay has varying rates, but ranges between 100 to 400 tons of carbon per kilometer squared per year. So we're seeing that sediment diversions might be that kind of act as crevasse clays might be really good at storing carbon. There's lots of other dynamics we still have to work into this, like erosion of the material that's there right now and where that gets transported to. But just the deposit itself seems like it will have pretty high carbon accumulation rates, which could potentially be used to get carbon credits to like offset the cost of some of these diversions. And it seems like any kind of river, delivering river sediment to areas might be a good restoration strategy, because that tends to be able to sustain the sea level rise rates a little bit better, and also stores carbon at a faster rate because it has really high sedimentation rates. So back to the three questions I posed at the beginning. Just to summarize, how does organic sediment influence the long-term evolution and dynamics of river deltas? Organic deposition creates a delta that's more analogous to field deltas with low slopes near the coast and more total delta area. So it's sort of important to incorporate wetland delta dynamics when you're trying to manage deltas and restore coastal areas. And then, what are modern rates of organic carbon sequestration in coastal Louisiana? We saw that the Birdsfoot has the highest rates of carbon accumulation, and they're actually far exceed these typical blue carbon environments with an average rate of around 300 grams of carbon per meter squared per year. And then lastly, what coastal environments have sequestered the most organic carbon over the Holocene, specifically in Louisiana? And our preliminary work shows that floodplain and crevasse clay deposits might have similar rates of carbon sequestration. And then these mouth bars, which are characteristic of deltaic deposits, sequester carbon super rapidly because they just have really high sedimentation rates. So with that, thanks, and I'll take any questions. And some of the work I've presented here is published in these two papers. So if you're interested in reading further about that, you can scan the QR code.
Great. So in your peers where you have finding organic accumulation rates that changes in grain size or
Yeah.
I was wondering, do you think that there's a mechanism there, or do you think that's
It's probably a bit of both. In the wetland, so I've drawn this gray line here that's sort of separating like wetland environments and non-wetland environments. In the wetland environments, that's probably really the process that's happening, and maybe the type of wetland, or how much, like if it's like super anoxic versus not, because that really depends on like how pristine the peat is preserved. If it's like really pristine peat, usually that's like a really healthy tidal wetland has like anoxic conditions versus some of these more mucky environments are maybe not like super high quality wetlands when they're formed. So I would think that in the wetland environments, probably processes. And then in the caustic environments, I think it's just deposition rate. Because I would lean towards it being more deposition rate, but that's something I could look like a bit more into.
Thank you that these can help us there. We also look at finding other things we make it, you know, like how those impact.
Yeah, you definitely can. I know like in the East Coast, for example, there's a lot of work that's been done about like tidal restrictions and how that impacts carbon accumulation rates. So in the East Coast, they have like lots of roads and dikes that block the tidal flow from getting to like one half of the wetland. And there's been lots of work that showed that if you compare the carbon sequestration rates in the area that's not blocked from tidal influence to the other side of the road, essentially, that they have really, really low rates on when they don't have that tidal influence versus the natural landscape. And then they've started to reconnect the tides to those wetlands that were blocked. And they've seen the carbon accumulation rates increase as the wetlands kind of being restored to its natural conditions. I'm not sure as much work that's been done specifically in Louisiana on that, but I'm sure that it probably has a similar impact. And it would be interesting to look at.
Your impressive map of the whole coast was a lot of work putting that together. But did I understand that you were like taking the fringe data and making that on a block and then interpreting?
Yeah, so I used a kilometer scale grid, and I used a spatial interpolation. I could go back to this, a spatial interpolation technique called Bayesian kriging. And we have a lot of, if you're really interested in like the specifics of that, it's in the paper, the method, but we have error estimates on all of these, or uncertainty estimates on all of these. So Bayesian kriging is really nice because it gives you uncertainty on your interpolation, and you can also use like cross validation to determine how well your model is. And we've got pretty good cross validation. So it is a large grid, but there's like 400 sites across the coast, so you can't really go much smaller than that. And we get some pretty high uncertainty, specifically on the sediment deficit numbers. But we've got pretty good control on the individual sediment properties themselves.
That was what I was gonna ask you. So I'll read the paper with uncertainty estimates out like.
Yeah, there is. So when you get to the sediment deficit part, which is kind of the main part of this paper, some of the sediment deficits are like, could be like 10% plus or minus like 20%, just like kind of high. So yeah.
Round of applause for our speaker here. Thank you very much.
Yeah, thank you.
Oh, yeah. We have a question on Zoom.
Yeah, she answered it. Oh.
Oh, okay.
So the first one is, how's the differential between fluvial and organic contribution used at present in diversion estimates being generated? So seems you answered it. Okay, there's a last question here. It says, walk us through how carbon credits mitigation could be used.
Oh, yeah. I guess the goal of this study for my postdoc is to determine if it's feasible to get carbon credits for sediment restorations like the sediment diversion. Obviously, the sediment diversion project is super expensive. And if we can show that it will store more carbon than the current environment is storing, there's a potential to get carbon credits for that. And our work is funded by Restore. I don't have like a good policy background, so I don't know if I can specifically answer that, but we're trying to set up this or calculate kind of a regional carbon budget just to give information about that and see if it's even feasible. I don't think right now, at least in Louisiana, there's any sort of carbon credits for any coastal restoration work. I could be wrong about that, but I don't think that exists yet. I hope that answered the question.
Thank you, everyone. Thank you for coming. And next week we'll have a special seminar because we have Dr. Brent Stomer coming. He's an assistant professor of biology at the Department of Biology, Jackson State University. And he will be talking about the marine science research at Jackson State University, the progress and the challenges. So I believe we could come and we could even have a chance to collaborate with people in Jackson State University, especially the faculty. So thank you very much for coming, and please sign in your name and enjoy your lunch. Have a good day.
Not only for